Hello, my name is Simon Blackmore. I'm a professor of robotic agriculture at Harper Adams University, and I'm currently working at the new Agri Epicenter based at Harper Adams University. My area of specialization is agricultural robotics, but by training I'm an agricultural engineer, and I've spent many years working on precision farming. But my particular interest at the moment is to develop new machines and techniques and processes to be able to make the whole crop production system significantly more efficient. And to be able to do that, we're then using the latest technologies to allow us to understand the growing crop in a better way and to be able to control what we do to the crop to allow us then to have the good food that we want and the more precision that we then need, which then will be environmentally more sustainable and effectively then to be able to feed the planet in the future. Thank you for having me. It's a great pleasure to be here. Thank you also all those who presented this morning. As an academic, I find a great pleasure in learning, and you taught me something this morning, so I enjoyed that. I know the difference between sessile and peduncle oaks now. But how many of you are interested in agriculture? Lots. Good. Okay. Right. Just want to make sure that I've got the context right here, because you spent a week thinking about plants and biology and so on, and I'm going to divert you a little bit over the next 45 minutes into machines and sensors that we can use with plants, mostly in the field, not in the laboratory. I'm an agricultural engineer. That means that I'm 60% engineering and 40% biology. But I've always been interested in measuring things and working in agriculture. And to me, the ultimate form of this interest then comes out in terms of robots. How smart can we make these machines to be able to work with plants? And that's effectively what this is all about. We've got an agricultural system, we've got a crop production system. We have to have, or we use machines to help us to produce plants and control plants and nurture plants and kill plants and harvest plants. And those machines that we're using at the moment, I reckon, are pretty dumb. And so my vision is to come up with a new mechanization system that uses all the technologies that we've got from, most of them are being developed from outside of the agricultural sector, but which are the most appropriate ones to bring into the agricultural sector, and which ones can we then use to help us then make the crop production system more efficient than it is at the moment. So I don't think there's anyone here from Harper. Or we'll have to look at that next year. Okay, Harper Adams, we're a very small university, but we're doing quite well at the moment with all sorts of student prizes. We've set up the National Centre for Precision Farming. We do a lot of work with drones. I'll talk about them in a minute. Autonomous tractors, laser weeding, robotic seeding and spraying. These are the projects that we've got running at the moment in this area, some of which I will talk about, some I won't, because this is my introductory lecture, or in fact, it's really the systems overview that I'd like to be able to introduce to you today. You might be aware that the government has invested quite a lot of money recently in agriculture. We've now got 4 new centres. We've got the Crop Health Centre, the Animal Centre, the Big Data Centre, and the Agri Epicenter, which is what I'm part of now at Harper. So the government's put 18 million into this new hub to help the agri-food sector to develop more. So it's very much in line with the things that I'm talking about today. We're getting a lot of interest from companies and farmers and so on to be able then to develop these different new technologies. But of course, if you are interested in agriculture, then There are a lot of challenges that we've got, and we've got to try and think about coming up with an agricultural system that is more pertinent to today's needs and in the future. And if we look at it from a systems point of view, we can then think about the strengths and weaknesses. And as I've gone through this development, I'm becoming more and more critical of the current agricultural system. Modern agriculture uses too much energy. We damage and repair the soil each year. Some of these I'll replay a little bit later on. Chemicals being wasted, going off target, causing pollution, large machines and practices damaging the soil, growth through economies of scale coming to an end. I'll deal with all of these. But we can see in agriculture that we've got quite a number of drivers for change. So we're trying to make a more sustainable production system, improve on-farm economic viability, have desire to have less environmental impact and so on. So there's a whole range of things. So about 10 years ago, I started with a blank piece of paper. I thought, right, well, let's come up with a new system. Let's try to develop the machines that farmers need today or need in the future that then help the farmer to achieve what we all want them to achieve, but also in terms of these drivers and legislation. And the one thing that I've come up with all of this work is that crop production has to become more flexible and efficient than it is at the moment. Many of the operations that we do now and the way in which we treat the crops is limited by the machines that we use. We're doing the same thing everywhere. A lot of it going off target. It's all based on cheap energy. But if we can then provide farmers with the tools to become more flexible and efficient, then I think the whole system will become significantly more efficient. And one of the main aspects of the work that I'm dealing with now is what I now call intelligently targeted inputs. So if we've got a farming system that's a bit sort of like a prairie and big open fields, it's a little bit like an industrial production line. So what we're trying to do, many farmers have the aim of maximizing production. Large tractors doing the same work everywhere based on a blanket application of energy. Now, one of the interesting things from a systems point of view is the ability to look at things from multiple perspectives. So I've tried to do some of this with some of the robotic work that I'm doing, but one of the most useful perspectives that I find when looking at this is actually the energetic one. So instead of, say, looking at it from an economics point of view, look at it in terms of cost and monetary items, then look at it in terms of energy. And we know that the current system uses a lot of energy, but what happens to it? And we can see that it comes in a lot of different forms. So we've got diesel in the tractor, we've got the energy going to make the tractor, we've got the energy going into the chemicals and the fertilizers and so on. And that energy then has got a number of different aspects to it. Obviously, if it goes on target, it's then useful. If it goes off target, then it's expensive, the farmer's paying for these things, and it's then being wasted, and it's then going into the environment, often causing pollution. So an energetic perspective is really quite useful. So at the moment, it's based on a blanket application of energy, but many industries have moved to what's called flexible manufacturing, react to changes in real time based on current conditions. And we need to do that in terms of the weather, the soil, the prices, and so on. But it obviously becomes a lot more information intensive. And so part of our work has actually been looking at the management of agricultural systems and to try and work out what the aims and objectives are from that management process. So sometimes it will be to maximize gross margins, manage risk, minimize environmental impact, and so on. Now, I'm sure you've all seen tractors getting bigger all the time. There's very good reasons for this. It's called economies of scale. So if you're going to pay a person to sit on a tractor for 1 hour, working in a field, if they can do 20 hectares rather than 10 hectares, then obviously that's an economy. That's a way of saving money. But in fact, these machines have now reached maximum size. Anyone care to take a guess why tractors and combines have reached a maximum size? Have a go.
They wouldn't fit through gateways and roads.
Correct, very nearly. Yes, there's somebody up the back there? Soil, okay, that's a very good point. I'll come back to that. No, they could be made bigger. Somebody else wanted to have a go? Okay, no, it's something a little bit odd. It's got to fit through railway tunnels. Here you can see a tractor being loaded onto a railway wagon, and in the back there's something called a gauge. And it has to then fit through that gauge because it then needs to go through railway tunnels, so as they move them around. If you look at the combine here, see it's got the chamfered sides on the top there, and that is again to fit through the railway gauge. So it's very pragmatic, the reason why these machines have been are now limited, but you're quite right that there are all sorts of other agronomic factors. So we've had big tractors and big implements, increasing work rates, reduces driver costs, cost and time per hectare. They're large capital investment, reached maximum size due to railway tunnels. Good for large fields, cannot be used in smaller fields. Now, again, a lot of my work is disruptive. It's changing the system a lot more than is comfortable. But I think it's right that we should change our mechanization system. And if your role, one of your roles is to help feed the planet, then obviously you're going to look at this from a majority of you from a biological point of view. I'm trying to do this from an engineering point of view. So let me paint a slightly different scenario for you here. We've seen the fields and the tractors and the machines getting bigger all the time. These are very efficient. They spend very short periods of time moving quickly across the field. But it's only the big fields and the big farms that can use the big tractors. And there are a lot of small farms and small fields, not just in this country, but around the world, that can't take advantage of that. So how are we going to be able to feed the planet? Where is this extra yield increase going to come from? Well, I believe that with the use of small, smart machines, we're then capable of increasing the efficiency, the crop production efficiency, for the small and medium-sized farms and the family farms rather than the bigger farms. So what I'm saying here really is that we're all playing different parts in the same system, trying to make agriculture more productive and to be able then to be better economically and of course then to feed the planet. One of my favourite pictures, I am an engineer and I do love big tractors, and give me a day off and I'll go out and do some recreational tillage with nice big John Deere and get it in the ground and get some black smoke coming out the exhaust pipe. I'd be very happy to do that. But the gentleman at the back there was concerned about the soil. What's wrong with that picture? It's stuck, yes, all right, we got that far. Why is it stuck?
The soil's too soft.
Sorry?
The soil's too soft.
Good point. That's what most farmers say, or that the soil is wet or something like that. But there are other factors as well.
Oh, it hasn't spread its weight out.
Sorry?
Like spread the weight of the tractor.
Okay, spread the weight of the tractor. Somebody?
And there's two types of soil?
Types of soil?
Yeah.
Yeah. Well, spread the weight is a good one. In fact, the way that I would, what many farmers will say, it's a stupid driver. So you shouldn't have driven there in the first place. But you're right, you're alluding to it, the tractor. Now look at that as a system. Can you change, well, a lot of farmers will also say that it's the weather. Can you change the weather? No. Can you change the soil? No. Can you change the tractor? Yes. The tractor is the part that we design and build. But yet, what we tend to do is blame the soil or blame the weather or blame something else. So, in fact, what we ought to be doing is making machines that suit these conditions. And that's part of the issue, that at the moment, these machines are getting bigger all the time, one size fits all. Often they're underutilized, so large tractors doing small work, rarely using full power. Boys' toys, big shiny tractors are always impressive. If you ever go to the agricultural shows, there'll always be a group of people around kicking the tires when they're up like that, because these are most impressive. But I reckon that small smart machines are also pretty fun. But there is an interesting part to this thought process, and that is that it's something that I call a self-fulfilling prophecy. You talk to any farmer, and they're always going to be saying they're up against the weather. It's going to rain on Thursday. I have to be able to deal with all this, that, and the other. But the smaller working window needs a bigger machine. He says, I've got to get all this work done before it rains. But the bigger the machine, the smaller the working window. And therefore you then say, oh, well, it's got to be done quicker than that, so therefore I need a bigger machine, and I can't. This is just going over and over again. So part of the work that we're trying to do here is to break open these old assumptions and see how many of them are valid and how many we can then come up with new methods. And particularly then, horsepower doesn't help when weight is the problem. We cannot change the soil or the weather, but we can change the tractor. So we've already mentioned then the issues of compaction. So here we've got the plough layer here from here to here, and then we've got a compacted layer underneath there that's then stopping the development of the roots for sugar beet. And what's happening then is that the machines are compacting the soil, but then we're ploughing or cultivating in here every year, but it then becomes, the amount of energy that we need becomes exponential as we go down with depth. And so it's very, very hard then to break up these lower layers. I now estimate up to 90% of the energy going into cultivation is there to repair the damage caused by the large machines in the first place. Think about the cultivation, think about all the ploughing, harrowing, rolling and so on. What's the purpose of that? It's to break up the soil. Why do we need to break up the soil? It's because in the previous year we've compacted the soil. So every year we compact the soil, every year we break up the soil. This is crazy. So we've got to come up with ways in which doesn't compact the soil, because it's repeated every year. If we don't damage the soil in the first place, we don't need to repair it. And of course, the natural soil flora and fauna produce the ideal soil structure. Okay, you're all clever people. Let's see if we can find another topic for you or for us to agree on. Where do you find the best soil structure? Oh, you're thinking. Yes.
Molehills are quite good.
Molehills could be.
Could be a garden, it's nice and aerated.
Well, yes. Not perfect, but good, yes. There is a better place. Yes?
Down around the bottom of the hill, so the nutrients run off the hill to the bottom side.
Well, remember I'm talking to structure, not necessarily nutrients.
Like an aerated structure then?
Yes, both molehills and aerated structure is a...
Compost heaps?
I'm thinking of something natural.
I know that they're not quite common, but normally volcanic soils.
Sorry?
Normally, like volcanic soils should be quite good.
No, it's an ecosphere. It's an environment, actually, what I'm looking for.
Around deciduous forests.
Good man. Exactly right. Yeah, forest. So in the natural flora and fauna in the forest ecosphere comes up with the ideal soil structure for plant production. And so, again, it's a bit crazy that every year we're disturbing that soil. We're then disturbing the ecosphere there. and then creating it with all this extra energy that we don't really need to do. Best thing to do, let the worms do the work, let the natural flora and fauna within the soil to give us the structure that we need. In fact, again, if I try to reflect on an aim of all of this work, is what is the minimum amount of energy that we need to introduce into the natural environment to turn it into productive agriculture? That's what I keep thinking about each time. Rather than all of this blanket, rather than just knowing exactly at the right time and the right place in the right way what should be done. And in fact, that's what you do in your garden. When you go to take your weeds out, when you go and plant the seed and so on, then all of these things are done individually, and that's what I think that the robot systems can do. We can move towards something called controlled traffic farming. There's quite a number of experiments around the country in that area. But particularly, I'm interested then in ultralight machines. So this brings us on to the concepts that I've been developing. So these are all just computer graphics. We haven't built these ones yet. We've built different versions of them. But it comes down, Massey Ferguson were good enough to sponsor the graphics. But it comes down to 4 stages: establishment, crop scouting, crop care, and selective harvesting. So here we've then got establishment. So that will include then things like what's needed for cultivation. Okay, we've got bare earth here, which is not necessarily what I would advocate now. So, but that's then putting seed into the ground in the right conditions. This one is then measuring what's going on, so that's the crop scout. I was intrigued this morning for the group that was doing the crop modelling and the computer generation. If you're interested, I've got another few slides that we can, if we've got time later on, we probably won't. But I'm doing a lot of work at the moment on crop phenotyping, robotic phenotyping. So how do we get these machines out there measuring all the characteristics that you're interested in terms of these plants? And I've been doing some work with a group in China. Probably have any of you seen Avatar, the film? Were you impressed by the vegetation that they had there? Well, the models that they used were actually then used, or the parameters were then adjusted for agricultural crops. And what we're now able to do is to use LiDAR systems and stereo vision and different non-contact solid-state sensors to be able then to take measurements of the plant and be able to recreate plants and then combine it with those models. There's some really interesting work going on in that area because you're all, I'm sure you've done a lot of it this week, you're all interested in sampling. And you're aware of the issues of sampling. How would you like the possibility not to sample, but to measure everything? That sounds a bit weird, but yes, you can. We can now measure leaf area to a square millimetre. We can measure every part of a leaf. We can get a hyperspectral response from every part of every leaf. We can measure every leaf in a crop. We've never been able to do that before. So this is quite exciting in terms of these new sensing systems. So this one here then is crop sensing. This one is then crop care. So some plants within the field we want to kill or to diminish, i.e. the weeds, and others we want to then nurture and flourish, which then are the crop. And then over here we've then got the harvesting system, or what I now call the selective harvesting system. I'll talk about these in a little bit more detail in a minute. So that's the overview of the system. So it's a systems concept to help improve sustainability, increase in food production, lowering the cost of food, reducing energy, protect environmental services, and so on. So let's look at the concept of the seeding system. We're coming up with some new terms again, which tend to be a little bit radical. Ultralight, very low draft force or zero draft force. What do I mean by draft force? Well, you've all seen a tractor. You've got big wheels on the back, small wheels on the front, and the tractor is about traction, and that means you're dragging things around. You're pulling bits of metal around the field. The interesting thing is, for every kilonewton of force in the horizontal direction, you need 2 kilonewtons of force in the vertical direction, and that is what is killing the soil. So, for me, one of the fundamental aspects of changing this agricultural system is that we've got to not have draft force anymore. So immediately then you might say, well, how do you do ploughing? How do you do harrowing? How do you do all of these different things? Well, my answer to that is that we don't need to plough. If we look at this, as I've said, from a systems point of view, then if we don't damage the soil in the first place, the natural flora and fauna will create the good soil structure for us, and we only need the tiniest amount of intervention of energy, so things like micro-tillage, to be able to give the right environment. If cultivate for each individual seed position, so if you've got a seed that's a couple of millimeters across, all that you're trying to achieve is about a cubic centimetre of the correct environment for that seed to then engage with its environment and to then flourish and grow. And so why do we then take the whole soil and turn it upside down? So there's a number of different methods. In fact, I'm working with 2 startup companies at the moment now in this robotic area, and one of them is then interested in taking these concepts and coming up with a robotic seeding system. So micro-tillage, cultivating for each individual seed position. That might sound a little bit extravagant. In this other presentation on phenotyping, no doubt you've all heard of GPS. Some of you might have heard of RTK GPS. And that means that we can get signals from the satellite to give us accuracy to 2 centimetres. How far do plants grow apart from each other? More than 2 centimetres. We can identify the position of every plant with an RTK GPS. In fact, about 10 years ago when I was working in Denmark, we built the first seed mapping system. So we took a standard seeder and put the electronics on it, and when we went out seeding, we could measure the position of every single seed that went into the ground. So 10,000 seeds per hectare for sugar beet, and we knew the position of every single seed that went into the ground. And that was done on an old 486 laptop. So yes, that's complex for us, but for the computing systems, then it's just very simple and very straightforward. We've got the concept of permanent planting positions. Do you want to plant in the same position each year? There are some advantages and disadvantages. We can do that. We can use vertical or rotary seeding methods, punch planting. There's nothing new in punch planting, that's been around for many years, but we can use those techniques again. Seeding depth to moisture. So what we're trying to do again is look at all of the agronomic requirements and then come up with machines that will do a better job of it for us. So a couple of years back I challenged my master students to come up with a machine that had less than 40 kilopascal or 6 psi pressure underneath the contact patch, which does no agronomic damage even at field capacity. So I've got a friend in Finland, Laura Alakuku, who did some work a couple of years back, and she reckoned that less than 40 kilopascal wouldn't do any damage to the soil. So the students then took we bought a ride-on lawnmower, 2-wheel drive, 4-wheel steer, so it's quite manoeuvrable. And they robotized it, and when the tractor stopped out here, I went to walk out to it, and maybe just down here, you can see a puddle, just see a little shine there. And what happens, I stood out there, this was in February, and it was at field capacity. You all remember what field capacity is? Anybody? Nobody? Okay, field capacity is not saturation, it's not flooded, but the soil structure is saturated. So you put 1 litre of water into the soil, 1 litre will then come out. It can't hold any more water. Often the soil is at field capacity. In the wintertime in Northern Europe, it's very soft. That's the real issue. So I stood out there, and the day after, then we've got a puddle here, meaning that the infiltration rate then has been stopped or inhibited just by the pressure underneath my foot. But in fact, where the tractor had run, up and down here, there's no puddles. So it's almost inconceivable for a farmer these days to think about going out with the tractor and putting seed into the ground when it is so wet. But if you want to put sugar beet into the ground at, 4 degrees C, then that's at the time of year where it may be at field capacity, and it may be then that you can't get out there. The farmer then has to wait until the soil has dried out enough to be able to support the tractor. So I think that this is not necessarily a good situation. We should come up with the tools that allow us to do the things that we want to do from an agronomic point of view without being restricted by the machines. So crop scouting. So we've got the ability to measure all sorts of different things within the field, working with the agronomists to be able to give a new set of data and information. We've got unmanned ground vehicles, phenotyping robots. I'll give you an example of some of these in a minute. Scouting robots. But we can also do it from the air as well. So there's a lot of interest in drones at the moment, which is what I call a rapid assessment technique. So if you don't know anything about the field, you can fly over very quickly. You can mosaic all the images together to give you quite a rich data set of information about the field, either through visible wavelengths or non-visible. We've then got NDVI, thermal, multispectral, and so on. But often the sensors are limited by weight and power. But they're not limited by weight and power when it's on a ground-based vehicle. So we're developing at the moment what I call second-generation drones. So first-gen drones are those where you can just control it from a handset and fly around. Second-gen drones are actually able to do things then rather than just take pictures. So, we've got a special interest group for drones for farming. A lot of drone pilots from outside the agricultural area are interested, so we give them agricultural training. Picocopters, tiny little things that you can hold in your hand, up to megacopters. Tethered, self-docking, automated logistics, and so on, machine-to-machine and swarm robotics and so on. There's a whole range of these different things. Okay, so the second generation drones are then drones that can actually do things. So this is a spray drone. So we've got the drone here, and underneath here we've then got 4 nozzles and a tank here. Unfortunately, we're not allowed to use these in this country because of the legislation. The legislation says that it's got to be applied in a certain way. But we are lobbying the government to make changes to the legislation to allow us to use it. They're not necessarily against this. The Civil Aviation Authority and Chemical Regulations Directorate are pro-drones, but only when they're used in the right way. So what we need to do now is to or what we are doing is testing these drones to make sure that they apply the chemicals in the right way, in which case we can then change the legislation. So the Agricultural Drone Centre, it's part of the NCPF, working with the different organisations to allow us to use these things. So here's a phenotyping robot that we made a few years back. It's based on a quad bike, and then we can robotize it. This particular one is for crop scouting for vineyards. So it's now out in the University of Athens, where one of my old PhD students is working. And we take an existing vehicle, and as I say, we robotize it with something called Sapphire. software architecture for agricultural robots. So we've got all of these different machines, but to me the challenge is how do we get that machine to, well, it'll never become intelligent, but how do we get it to become more intelligent than it is? How do we put the smarts into a machine? That's all done through Sapphire then, but we've also got a range of different instruments on there. So we can use thermal cameras for irrigation status, so we can look at the temperature of the leaves. So when the stomata is open, you're getting evapotranspiration, you actually get cooling of the leaves. But when the stomatas are closed, then you get warming of the leaves, and the leaves come up to ambient temperature. And so we then know a little bit about the plant and whether it then needs more water or not. Multispectral cameras, we can then use non-visible wavelengths to be able to look at the chlorophyll. There's a direct relationship between chlorophyll and nitrogen, and we can work out then whether we need to apply more fertilizer or not. And then we also have this system LiDAR, which is laser range finding, and we can then be able to measure the canopy extent and the density. We can work out the biomass that is there just by using LiDAR systems. So let's come on to how to kill plants. So here we've got obviously lettuces here, and these are the weeds that we now need to control. And there's lots of different ways we can kill plants. Mechanical weeding, microdroplets, laser weeding. So again, this is years back in Denmark on the first autonomous tractor that I made. We've got RTK GPS on the tractor and on the side shift toolbar. And we've also then got something called a cycloid weed hoe here. And what's happening is that we know the position of every plant, every crop plant, and the cycloid weed hoe goes along here and it withdraws the leg when it comes to the plant. And so we can do the inter-row and the intra-row weeding, although a couple of these ones aren't going to make the grade, I don't think. But there's no artificial intelligence in there. That's just straightforward deterministic control based on we know where the plants are, and so therefore we avoid those areas. But you've still got a big tractor there moving along, stirring the soil where you don't need to stir the soil. So from an energetic point of view, that's still wasting a lot of energy. Some of my old students in Denmark went to go to work for this company, Kongsskilder then, and then they've come up with the Robotic. And again, this is just a prototype, a toolbar that then just can go through the crop, and that's just doing mechanical weeding. Again, this is a PhD student of one of my old PhD students. I don't think the sound's coming through here. So what we've got here is a token weed, and we're going to put this through the system to do what I call then intelligently targeted inputs. So we've got a hood on here with bulbs in there. We've got a camera on the top, and underneath there we've got a little spray boom across there. That's an inkjet printer head for cardboard boxes. So very simple technology. And he's going to put it into the robot arm and pass it through there. So you can see he's got a computer, but again, it's not a supercomputer, it's just an ordinary laptop. And you could see the plants going through there from the machine vision system. And what I want you to do is to just look on the leaves. Can you see some blue on here and here? Now, here, this is an interesting factor here then. So, what do we do at the moment? We have a 36-meter boom sprayer, and it goes across the field, and it spreads the chemical anywhere. or everywhere. How much of that goes on target, do you think? Give me a percentage. 5, yeah. It's as low as that, exactly right. For the selective herbicides, it'd be 1, 5, 10, something like that. So what's happening to the rest of that? It's all just going onto the crops, going into the soil. Farmers having to pay money for that, and it's totally wasted, and it's causing pollution. This is crazy. And in fact, you might be involved in discussions or be aware of discussions later this year where there's talk of banning glyphosate and banning a whole range of chemicals, because we think, okay, well, chemicals, they pollute, they cause problems, so we should ban them. Again, I say something radically different. There's nothing wrong with the chemicals. Nothing wrong with the chemicals. Let's ban the machines that apply the chemicals in the wrong way. Now look, what we've got here is the ability with a webcam and an inkjet printer head to be able to reduce the amount of herbicide that we're now using, reduce it by 99.99%. Same chemical, same plant, all that we've now got is another little machine that goes out there and does things slightly differently. Now, this is the opportunity that we've got to be able then to come up with another piece of the jigsaw of the new system. Now, this is the video that the farmers love, because there's 3 poor little weeds in a pot there, and then we're going to get the lightsaber out and we're going to do them mischief. But there is some science behind that, and that is that we can use machine vision to identify the meristem, and then if we heat the meristem up to 95 degrees C, the cell walls then rupture, and the plant then either becomes dormant or dies. In fact, some plants, and you'll probably tell me which ones, will actually then generate new meristems and grow again. But if you think about that, many of the weeds in Northern Europe are herbicide resistant now, and the chemical companies are not developing new active ingredients. So how are we going to control these herbicide resistant weeds? Well, we need these physical methods, and laser weeding is one of the areas that we're working on. So I can't show you the current work we're doing at the moment, but it's field tests last week and this week doing the laser weeding work, but it's really quite encouraging. You'll find these videos on YouTube if you're interested from the original work. Then we can come to the autonomous tractor. So we've built, this one is the Pomona tractor. What it's showing is that it's under RTK GPS, and it's got something on the called LiDAR on the front there, and it can then switch between absolute positioning to relative positioning based on the obstacles in front of it. And you can see all the other different safety systems on there. So we've got, that's the first autonomous tractor. We've actually got a second autonomous tractor now working in the hands-free hectare. I don't think I've got a slide on that, so I'll just tell you about that. Years back, there was, in America, they had a number of in the research industry, they had a number of what they call grand challenges. And I thought, what's the grand challenge in the agricultural sector? And to me, that was then to be able to grow a complete crop, go through a complete cropping cycle without anybody going into that area. So I used to call it the autonomous acre. They now call it the hands-free hectare. They want to go to SI units, so it's the hands-free hectare. But we have a hectare at Harper Adams that has now been cultivated and seeded and fertilised, and they're now robotizing the combine harvester to go in. And the idea is that we've got our own brewery, so they're actually going to make robot beer from the barley. But yeah, so we've got quite a number of these different machines able to do this. So Finally, I come to what I call selective harvesting. So there's quite a number of different issues here. And that is that, first of all, the major growers harvest in a particular way. It's what they call slaughter harvesting. They go in and just take the whole crop out. But from the work we've done on precision farming and the problems that they have, which is about, we know about spatial and temporal variability. So we know that the plants will thrive in some areas, are then retarded in others. Some will then be more advanced and some will be further behind. So what they're trying to do at the moment is come up with systems that will be able to give a totally uniform crop. In my point of view, that's fighting nature. I think that we should go the other way round. We should come up with a cropping system that matches nature and allows us to take into account all of the variability. I estimate between 20 and 60% of the harvested crop, or they estimate, is thrown away at harvest. 20 to 60% of the crop is thrown away at harvest. I mean, this is ridiculous. Do you know why? Well, ladies and gentlemen, I'm afraid you're the problem. Because what happens is, and I'm the problem too, the thing is that when you go to the supermarket, you see your tomatoes, you see your lettuces, you don't pick the worst one, you pick the best one. You're doing selective harvesting. So what happens is that the supermarkets then won't buy wonky vegetables. So the farmers then have to grade them before they go to the supermarkets. But what we're trying to do here is then to come up with a system that only harvests that part of the crop which has 100% saleable characteristics. So if we can sense if that lettuce in front of us is of has saleable characteristics, then we will harvest it. But that also leads to a whole range of other different opportunities. Then phased harvesting, possibly even immediately replacing with a seed or a seedling. Pre-harvest quality and quantity assessment. One of the aspects of selective harvesting is the ability to grade at the point of harvest. So that what I'm trying to do is, I'm on the side of the farmer all the time, trying to increase value to the products before they leave the farm. If you look at the whole food production process, you will find that the poor old farmer right at the beginning has got the least margin. When it goes to the processors, the transport and the supermarkets, they're all making significantly more money than the farmer. And I think that with these type of techniques and tools, we can add value to the on-farm products, particularly by grading them before they leave the farm. So there's the concept machine. And in fact, it's two machines here. So the front part here is the harvester, and the back part there, you could call it the trailer. There's another aspect to this, is what I call automated logistics, because the harvester can then use LiDAR, multispectral cameras, whatever, to recognize the parts to the crop that it wants to harvest. It can pick that up. It can then take it through, wash it, crate it, whatever it wants to do, and then push it through into the back here. And when this is then full, this can disconnect itself, it can run away, and another one can come and plug itself in. But it's then got all the water and the fuel and everything to keep the front part running. So although we think of robots as a particular machine, it is a system and it does have to then be supported. But what we can see here is that some of the lettuces are small down here and we're leaving those behind. But because we've already measured them, we know how big they are and we can estimate when it's right that we can come back and harvest them again. So this thing of phased harvesting then allows us to have a much more profitable crop and be able to utilize more of that crop than just throwing it away. So we've done some work on a robotic strawberry harvester. Maybe you can just see that there's two images here, one here, one here. So as we have two eyes, we can judge the depth. We have two cameras that can then recognise the peduncle and be able then to work out well, first off we work out which ones are ripe and which ones are not. Secondly, then we can work out which are the large ones, which are the small ones. And then thirdly, we can then recognise the peduncle in the two images and be able then to come up with a depth, and the robot can go and then pick it. So in conclusion, I'd like to just say that mobile robots will be used commercially in the arable and horticultural sectors. It's more likely to be introduced in the high value crops than the low value crops because of the investment. It'll be very disruptive, but will have significant benefits. And I think increased yield will come through improving smaller fields. We're now designing the new systems and trying to understand the implications of this. But I'm always interested in partnerships and having discussions with people, particularly from other areas, to help us understand how this new system can be made more practical and find a way quicker into commercial agriculture. So with that, I will say thank you very much for your attention, and I'll be very happy to take any questions if there are any.